All right. First, let's do a little bit of practice. You can request control and take a nano diffraction pattern in the STEM mode. So I said first you need to go search and find the region of interest, and then you can park beam on the region of interest, and then you can insert the SATA camera to take an image from SATA camera by using the SATA camera.
Okay. Because right now it's in diffraction mode, right?
Right now it's in diffraction mode, in STEM microprobe mode. You can still, if you use quick search, you can use the either Vlogs or you can use the TA to take a look at the to find the region of interest.
Okay.
So
let's look at TIA then.
Mm-hmm.
I'll just hit search.
You hit search, and then probably you need to, let me select the view for you. Select the TA software for you. This is your view. You see image. You can use scope tool to increase contrast. This is probably good enough. Okay. And I can move a little bit. Zoom out.
Let's move up.
Move back.
We could zoom in.
Mm-hmm. You can do a scan notation. Okay.
Okay. And
For me?
No, I just need to look at this. I need to throw in the beam. So let me see.
Yeah, this one.
Just this one. Okay. We can zoom in more, I guess.
Yeah,
focus a little bit.
Okay. Need just maybe stick measure.
Okay.
You can increase a little bit of dwell time. Okay.
Okay. So you just want to go into the diffraction mode?
Yeah.
Wait, where's the beam? Oh, it's beam there.
Yeah. So first you need to stop the view. If you want to see the beam and see the diffraction, you can go like here. When you stop the view, once you stop the view, you can drop the beam. You see, you can move it around, right?
Yes. Okay, you just park it there.
Mm-hmm.
Okay, and then
Yes.
Okay, so we have that.
Mm-hmm. Nice.
So this is, we can sharpen this
Yeah.
image. Get a better focus.
Focusing?
Yeah. So you want to, so, okay, this is already in STEM. So you wanted me to get a diffraction pattern while it's in nanobeam or a microbeam?
I want to get a diffraction pattern. So you want to use the CT camera to get the nano diffraction pattern. So you cannot adjust focusing after nano diffraction because it's the focusing so bigger because right now if you adjust focusing, you add focusing of image, not your diffraction, right? So go here. You're adjust your focusing, not the diffraction. So, but another sense you can adjust a little bit if you say, but don't adjust the intensity. If you add the intensity, you go stem focus. If you choose, now it's grayed out. So don't adjust the focus is good. Consider focus you have. So you don't need to adjust focusing of your diffraction pattern.
Okay.
Yeah.
So then you adjusted it a little bit, right, earlier, or no?
I adjust the focusing, but that focusing not control your diffraction pattern. It's control your focusing on your stem image, right? If you do search, it control focus on your stem image.
Yeah.
Okay. So let's say this is the region, and then what should we do?
We'll take off the half the detector.
Right. Get a more view.
Okay. And then since we're in STEM, we don't have to put in the beam blocker, right?
Yeah.
Okay. Guess at least we could probably let's center this.
Sure. Happy to do so.
Right, to the middle. Get the bright spot in the center.
Mm-hmm.
Okay. Well, let's go. We'll switch over to Tia. Then should be able to search. Wait, how did we use the?
Because you take a detector off, right?
Yeah, are we using the SATA camera?
Yeah, we're using SATA camera to do preview of your SATA diffraction pattern.
Okay. Let's go over here. And then was there a reason why we did bin 4 earlier or no?
We do beam 4 because beam gonna shrink your image size, but definitely gonna increase your contrast signal to noise of your image because you get more count if you do binning.
Okay.
So you first need to select here. Go to now you're in Acquire. You go search first. You set out the choose search, and then you set up the acquisition time to be like maybe 0.05. And then check the quality. You can go binning 4. Go binning 4. Now you go pin 8. Set time to 0.0, yeah, 0.08, 0.008, 0.005, sorry. Start from the low exposure time, and then you say. Let me enter. Fine. Okay.
Okay. All right, and then we'll search.
And then you need to enter. Say enter. Yeah. Okay. And then leave the screen. Do the search.
Yeah.
Arrow. Let me see. Something goes. Should be good. Arrow this one. Let's restart. Let me restart this one. Okay. And then you can take the next stress. So non-profile.
Where's the line profile?
The first, click first one.
So is that 2000?
Yeah, 2000. Then it's good. Just use this one, and then you can set up binning for. You can go 0.05. You can do 10 frame. Yeah, it's good way to zoom in, and then you can get.
Okay. All right, so we have that. So let's do. It's about 2000, right?
Yeah.
So we can make this 0.1, 0.01.
0.01. Okay.
Be about 4000. Okay, and then we did high dose. Maybe so for search we did 0.01. One. Then we can do 10 frames. Right.
You need to enter to make it work. Yeah.
Okay. Double check. 0.01, 1 frame times 10. Okay.
Yeah, that's good. You can increase the brightness or gamma.
Oops. Okay.
Mm-hmm. Yeah, that's a good one. So so now you're familiar with the how to take a diffraction pattern, right?
Yeah.
Okay, cool. So next I'm gonna show you how to convert the beam diffraction patterning. So first, let's load screen and find the region. We probably use the camera. Double click. We go for different region. Okay, and then we stop the view. So we park the beam. Stop the view. Park the beam to different region. Okay, park the beam on the matrix. We take a look at our diffraction here. This is our diffraction pattern, right? So right now, if you take a look at beam setting, right now we're at the microprobe mode. Whereas the semi angle is about it's 0.6, right?
Yeah.
That's in that angle you cannot you cannot do converge beam electron diffraction. So we need to increase this angle. To increase this angle, we can try different aperture. So we can try different aperture at microprobe mode, and then we can try different aperture at the nanoprobe mode. First, let's do at the microprobe mode. So we go to 50. You see this value increase to like 1.5 something. So let's park the beam to different location. I like to use relocks. So acquisition is a just context to take a setting. Let's go to bring that down. Okay, just focusing. Okay. Stop. Okay. So this here, you see another beam diffraction and the natural. Okay, you see when you go to the 50, this is your diffraction pattern. This is your convergent beam diffraction. You see your central spot getting bigger. Your diffraction spot getting bigger. So, and you see some contracts. You see some contracts linear within the diffraction spot. You see here, like this is the integrated strain information within your diffraction spot. So this is a 50, and can you go further increase the convergence angle, and your diffraction spot become bigger and bigger. Right now, your convergence angle become like 2.1, and you can write this down this number. So and your convergence angle become 2.1. Your diffraction spot getting bigger and bigger. So let's go for largest. If you go further increase, your semi-convergent angle is 10 to 4.5. And then you see only one spot, because your diffraction spot basically overlap with each other. You see they're overlapping, right? So we will go one by one. We will go from 151. We will go for 20 first, and then take imaging, and then we go for 50, take another imaging, 70, take another imaging. We will consider this effect. We will get then they can compare the difference. So let's first move to the center of the sample to get a good region. We just go there to find a good region. So find a good region. Probably this is a good region for the nanobeam diffraction. Okay. Go here. Stop the beam. Move a little bit. You see this is very good then. So first we take image of this user 20. This is nanobeam diffraction, and you get semi-convergent 0.6, and then we can take out detector, or we can just choose smaller, probably smaller. You can choose smaller cameras. So in this case, you can increase more diffraction pattern. Probably go for like something like this. Okay. Take out your diffraction. Take out detector. Okay. This is your converge. This is your nano. Actually, this is your nanobeam diffraction, because your converge angle is only 0.6. It's very small. So let's say if we can. So you can use the full cam to get this image. You can just set the temperature. You can use high dynamic range. Go there. Quick center one. And just use full cam to take image. That's much easier. And then once say OK, we just do a snapshot. Get to this TA. Once get to TA, we need an adjuster.
So since the convergent angle is low, this is just normal.
Yeah, this is normal nano diffraction patterning. Okay.
So we don't have to be in nanoprobe. We could just be in microprobe when we do that.
Mm-hmm. So we can do that at nanoprobe. It depends on your what convergent angle you want to use. As you know, as you have already seen, because when we change the C2 aperture, you see your convergent angle change from 0.6 to like 4.5 something. So there's a lot of the convergent angle you can get in the microprobe mode. If you want to go for even larger convergent angle, you need to go to the nanoprobe mode. I will show you later how to go to the nanoprobe mode and how to get the convergent beam direction diffraction. So this is your diffraction patterning. This looks pretty good. This is a so we just use the you can also use the CETA camera to get another imaging, but it just you can go here. You can go set up the acquisition time, files, game model. You can go for let's set up the search first. 0.1 a coin gonna be 10 frame. Let's go 20 frame. Okay. And then we need to take a look how it looks like. So we do search first. So search. Let's go for 0.1, right? Okay, wow. Then we search. It's probably too much, and the 0.05. It's gonna be okay. 3.05. We do a coin. It's gonna be 20 frame 0.01 to 5. 5. So we go. Okay, this is the image, and then you can do this one. So this is the image. It looks like an exposure maybe. Okay, that's good. And then we can just put the screen down. Turn to the 50. We got, you see, this is your convergent beam electron diffraction, and then you can see grayscale. Look at it. You can just acquire, go to your TA, send to TA. This is your convergent beam jet electron diffraction by the flow cam. So it has to see there's some information inside. So if you want to see some information inside, probably good to go for this mode. See another image. Let's use the camera. Let's use the camera. You can just go for we set up to be safe. We just go for more frame. Go for 40. And then we can use the screen and acquire image. You can go there, just your image you acquire. Yeah, that's good. You say this is your spot get bigger. This is your at 50, right? This is the 20. This is the full cam taken by. So now delete the full cam one. So this is 20. This is 50. 50, you see your spot get a little bit bigger, right? Because your convergent angle getting bigger. So now your convergent angle is 1.5. You can go even bigger. You can go 70, and then you can put the screen down. This is the 70. You can go. Scale. Now your spot get even bigger, right? You see that something in the future within the disk, some contrast within the disk. That's something related to your screen. can do some string analysis there. And then you can leave the screen, acquire another image by use TA. This image you just acquire. So you see your spot getting, this is 70. You see your spot getting even bigger, right? So you can go further. You can go further. Also, you can choose the large camera lens, so you can get more information. Your field of view look big, so your spot looks bigger. Then you can go there, go to 150. So in this case, you can leave the screen, acquire another image. So this is your. So now you see your spot overlapped. You see your central spot overlap with each other. They overlap. You see, this is the one big spot. You have the spot overlap with each other. So when you get a semi-convergent angle 4.5, this is your overall image look like. See, you can acquire send it to TA. Okay, auto scale. You get some information within this disk. So okay, this is how we get the nano diffraction patterning, convergent beam electron diffraction with in the nanoprobe mode. So we basically control the semi-angle by control your condensed lens 2 aperture size, the select different size of C2, right? So this is how we do that. It's quite straightforward. If you know how to take diffraction pattern, nano diffraction pattern, you know how to take that convergent beam electron diffraction. You just select different aperture to give you different semi-convergent angle. So convergent beam electron diffraction usually have this angle larger than you see it's larger than several degree. It's gonna some people want to say the overlapping of the disk. Some people don't see the overlapping. So as we can tell, if we go for 4.5 semi angle, if you choose the CGF 150, you see that central disk get overlapped. So if we don't want to overlap, just go 70, you get a very good convergent beam electron diffraction. Your diffraction spot become bigger, and you can see some information within the disk. This is the strain information. So, and also, if you want to go further, we can go to nanoprobe mode. We can go to nanoprobe mode, and immediately if you go to use this, we can choose the smallest C2. If you choose smallest C2, you will notice the semi-convergent angle you get is 3.0 mean rate, right? It's actually not so bad. It's smaller than 4.5. So right now, if you semi-convergent angle is 3, I think this condition give you better imaging. Because your central disk become bigger, and also you don't have overlapping. I think this is gonna give you you can go there, you can leave the screen, use camera, acquire imaging, and this is your convergent beam electron diffraction pattern. So with convergent angle 3.0, you can go choose increase. So you can see, if you zoom in, you can see this. A lot of people indicate the reason they want to do convergent electron diffraction, they want to see some information within the central disk, within the diffraction spot. This is good, because if there's diffraction disk overlap, so the information gonna be mixed together. It's hard to tell. So usually we don't let them overlap with each other. So that means 3.0 million rate is good semi-convergent angle to achieve that goal. So we can go further. We can go 50, and then the semi-convergent angle gonna tend to somewhere between 7.5. That's pretty large. And in this case, you're gonna get a large convergent angle electron diffraction pattern. So that means that disk you can probably only see the central disk, and you look at the information within your central disk. So probably we can do the tilting here and move up. So it's not right at center. Okay. You tilt down a bit. Move to location. So we need to refine the sample. Of course, if you wanna get perfect convergent electron diffraction patterning, you need to find a good region and do very fine tilting.
So for convergent beam, the spots are all bigger and all brighter, right?
Yeah.
But the distance between them are about the same.
The distance between what?
Between the spots.
The distance between a spot is gonna definitely reduce. It's gonna become because the spots gonna overlap with each other. There's no distance between them.
Okay, but the goal is not to have them overlap, right?
The goal, if it depends your application. If you wanna just do the convergent beam electron diffraction patterning, you don't want the overlap. But if you wanna go for large convergent beam electron diffraction patterning, you want the overlap. You want to just see one central disk.
Okay, it's for different information, right?
Yeah, different information. So
can you give me some examples, or like why would they do like convergent beam versus like normal diffraction, and then why would they do convergent beam?
Yeah, usually people do convergent beam diffraction. They want to see your information from within the disk. They want to see such information within your diffraction disk. It's not just about the orientation. So usually people do diffraction. They want to know orientation, right? But what if you want to know more? If you want to know like strain information, how much strain you got, you can see this information within your diffraction disk. There's a lot of reference. I think if you search, it's better just look some read some paper. They have very good review on convergent beam diffraction pattern and related to different application. Some people use them for determining special strain they have within the grain or even special defect. Also, some people take a look at the polarization. So this is for different applications. So
Okay.
if you want to see something within the disk, the goal is to see something within the disk. It's not about something outside this, not just about the orientation. It's get more information within disk. Okay.
Okay.
All right, and then so we go to the semi-convergent 7.5, and then we can we say your disk start overlapping, and you see the central disk here, right? This is central disk. You move sandwich back to center. You want to have, if you want to go for that, you probably need to have very perfect orientation. You need to tilt your sample to the right zone axis. Let's do not do this. Let's do a little bit more tilting. Okay, looks fine. Okay, it's close. It's close. Let's see where I want. Okay. You see? Oh, let's do this. You can do a little bit shopping, looking around to find a good region. This is a very good region. Okay. Okay, and then you can just set up leave the screen, a coin. Oh, sorry, I hit that. Let's go here, coin. So you can see the information. This is the edge of disk. You see there's some information there.
Okay. Then you didn't take the haft out, right?
Yeah, I haven't. Yeah, good. I should take it out. And take it out. I recur not.
Okay.
This is 7.5, right? Now we can keep going. We can go to 70. And then we put screen down. You see this here 70 diffraction patterning, and you can go shopping around. Okay. That's how it's look like. And then you take it out. Get it out of there. Flip screen. Coin. Okay. So you say your center spot got bigger and bigger, right? So this is at F250. This is 70. So if you get a big center spot, you can see clearly more information. This one you can still see some overlapping of the. You see that you don't get a sense for how big of your diffraction spot is. For this one, it's totally you can only see one. I think you can only see one central disk right here. If you keep going forward, if you go further to the node 150, now you only see one central disk. I think. Let's move a little bit. Okay. Okay, this is right and okay. Then you take detect out. Leave the screen. Oh, sorry about that. So go here. So this is your. You see some some information there. So this is definitely one central disk. And compare them one by one. On the scale. On the scale. If you put them together, this is the 50. This is the go through then. So 20 aperture C2 at the microbeam. The convergent angle is 0.6. You see like a nano diffraction patterning. The key aperture convergent angle increases to 1 point something. You see your diffraction spot get bigger. And you can further increase your C2 aperture to 70. You see diffraction get bigger. And if you increase to 150, it's getting bigger and bigger, right? This is 150 at the microbeam. And then if you want to go further, you can switch to the nanobeam. This image we look at in the nanobeam with C2 aperture 20, right? You can see a lot of information with there. You can see, if you just want to converge beam electron diffraction, I think this is a good setting. You go to nanobeam, select the 20 FCH aperture. Another good setting is, I think it's this one. This is 70 C2 aperture microbeam. So this two setting is pretty good. And if you go further, you go to the setting 50 and 70. You see your center spot getting overlap. So, and this is largest 150. You see there's some add information, some French there. Okay, this is how we take converge beam electron diffraction pattern in the STEM mode. Okay, I recommend you do this converge beam electron diffraction in the STEM mode because in this way you know your converge angle. If you switch to TMO, we do converge beam, we do the same thing, we don't know the converge angle. So, but the trick here, if you switch to the TMO, basically you can choose different C2 aperture. You can apply it's like converge angle for stem and tan should be very similar. That means if you choose the same C2 for the stand and the 10, they should have very similar convergent angle. In this way, you can remember the value in the stand and then apply that value to the 10 as well.
Okay.
Okay, you want to do a little bit of practice on this one?
Okay.
Cool. Go ahead.
All right.
So, I want you to get two, like three diffraction. First diffraction, I want to see nano diffraction. You already take that diffraction, right? The second one,
I did it in
you
microbeam.
have already done that. Okay, good. The second one, I want to just see the diffraction. I want to still see a lot of diffraction spot, but I don't want the overlapping of diffraction spot. But I want to see as much detail as possible within the disk. But I don't want the overlapping of the diffraction disk.
Okay.
So you can choose the right setting to get that image. Go ahead.
Okay. So let's go back over here. Okay. Okay. All right, so let's decrease. Let's. Yeah, let's open the column though. Or pull down the screen first. Okay. Let's switch now. I'll do 20.
Yeah, that's good one.
Okay, and then let's see, stem. Let's take out the detector so we can see the whole pattern.
Mm-hmm. Good.
Yeah, I think this should be pretty good. All right, and then so we could go to, yes. Well, let's take a picture and or figure out the location. We can go to VLOX and then do a scan so we know what we're looking at.
This is a good one.
Okay. I guess we just take a normal picture.
Okay.
It should be okay. Okay. All right. Okay, so the spots we're looking at is pretty good. So we can go back over here. Take out the detector.
You can use the. How can I get a like big view of the diffraction disk?
Wait,
Now diffraction disk looks a little bit small. How can I make it bigger?
this?
Yeah. How can I make the
You
difference?
change the camera length?
Yeah. Perfect. Yeah. Change the camera lens. Make it bigger because I want to see the center information, right? Okay. That's good enough.
Okay. Yeah, let's center it. I think this is the center disk, right?
Yeah, I think so. It's the brightest one.
Let's bring it to the center.
Okay.
Okay. All right, so we got that ready. Then we could go to camera. We should, let's see. This should be pretty safe. We could just hit acquire after lifting the screen, right?
Mm-hmm.
So let's screen. Let's hit acquire. Okay, so it's pretty good.
Or you can increase a little bit of exposure time to 0.2.
Looks so dark. Because there's not enough signal.
You can increase a little bit of exposure time.
Okay.
Go to integration for the acquired prism, choose to be 0.2. But not 0.1, right? Go for 0.2. Also, still for the 40 frame. Enter. Yeah, that's good. And I acquire another image.
Okay.
Pretty good.
We don't see a lot of stuff, huh? Only see those.
Yeah, because your camera is very large, right? Actually, this is very good information. There, if you take a look here, okay,
I'm sorry.
it's fine. Let's say if you take a look here, this information there, it's very unique.
Okay.
You see here, kind of information like X. This is to indicate you have some string within your single crystal. Okay.
Okay.
Yeah.
Right.
Another one I want to go for. I just want to see one center disk. I don't want to see the others.
Okay. All right, let's pull down the screen here. Okay, we'll switch to 150. Okay. So it'll be one disk here.
Mm-hmm. Cool. Can I apply? Lift screen.
You'll probably have to do it again. All right, we'll go back to Tia.
Cool.
Then there'll be different information here, right?
Mm-hmm. You see the string.
Okay.
All right. This is how we take. Actually, pretty good. Okay. Maybe we can switch to the different sample. Go STL sample. Go there. and take a look at how that convergent beam electron diffraction look like. Now you see we a little bit tilting. Let's see how where the sample is, right? So I already got a searching view here in the widgets. So it. Put sample to the center height.
Okay.
Okay. So I want to take image one in here. On the sample without any contouring. One within this, because here you see some deformation. You should see some strain there. So let me stop. Okay.
Okay.
And then you can.
Okay. That. Then this is for.
Let's do the. But now they have overlapping, right?
Yeah.
I don't want to see overlapping. Let's do.
Let's go back to 20. Okay. So there's this, and then, do you just? So when you're in this, do you adjust the focus? You don't adjust the focus because you're in STEM, right?
Yeah.
Okay.
Focus good.
Okay. And then, okay. Then we'll just take a picture.
I need to leave the screen.
Yep, left the screen, and then I'll hit acquire.
Yep. Here's your information. And then you can take another one.
With more integration time?
Take it around on different region.
Okay.
So
we'll go back to VLUX.
So I want to park a beam around somewhere. It's on a, okay, let me stop the view. Go ahead. Okay, somewhere there.
Okay.
So check the detector.
Okay. And then just take a picture here. Screen's lifted. Acquire.
It's still different information, right? So
is it looped like this because it's at a non-flat surface?
it's not the on the zone axis. I think this one it's tilted a little bit, right?
Okay. Let's see if we adjust the brightness.
Mm-hmm.
We could check the Kikuchi lines if it appears, right?
Mm-hmm.
All right, let's see. We can put down the screen again.
What do you want to do?
We can't see the Kikuchi pattern.
It's on the top. If you want to pick which pattern, you probably go for stand. Choose a little bit. Choose smaller aperture. And again, natural. Okay. Now you see that, right?
So it's not turning. Okay.
So probably tilt back, tilt to the.
No, we're probably off the sample now too.
Let me do it. I just
okay.
Tilt sample back to the center. Okay, now this will be very close.
Yeah. You could probably move the beam and it'll probably be in the center. Whatever position it is on the sample.
Okay.
Okay, so we could try taking a picture.
Mm-hmm.
Okay, let me go over to Tia.
Oh, different.
Oh. Okay, I'll take the picture again. No, I forgot to do that as well. Yeah. And it's pretty small.
Because we use very small cameras, right?
Oh yeah, when we're
We need to increase the camera.
Yeah, okay. On the screen again.
Go to stand. Okay.
Hit the camera. To the screen.
Yeah, right.
Yeah.
You need to adjust contrast a little bit. Now you see your different contrast in different days. Definitely, in gender is not uniform.
Okay.
Nice.
Okay.
Yeah, this is how we do nano diffraction and the convergent reaction diffraction in the STEM mode, right?
Yeah.
So next, I think we got a couple things left. First, we can switch to the TMO to take a look how we can get convergent electron diffraction TMO. Because right now we get convergent electron diffraction at the TEMO, right? A STEMO. This is one thing. Another thing is I want to show you how to do nano diffraction or convergent electron diffraction mapping. So right now you did the single spot, right?
Yeah.
You collect the electron diffraction on the single position, right? What if we have a mapping? I want to collecting all the electron diffraction pattern on this mapping automatically by the software. It's like 40%. But here for the Talos, we don't have the directly electron camera, so the camera speed is not fast enough to get a lot of more information. But we can definitely can do nano diffraction mapping. So this is another thing I would like to show you. And another thing, if we have time, we can do a little bit more practice on how to get a good high resolution star imaging. So yeah, this is three things. Let's first take a quick break, and once back, we're gonna take a look there because we are in STEMO. Probably gonna take a look the nano beam mapping first.
Yeah. Okay. Let's do the mapping first, because I think the convergent beam for TEM is probably similar to what we did before, right? Just make a small probe.
Yes. Make a small probe and also choose different situ aperture to get different converge angle.
Okay.
Yeah.
All right. Yeah, let's take a break and then we'll go over the mapping.
First, yeah, mapping gonna take a little bit of time, but it's gonna be a very interesting application for you.
Okay.
Okay. Yeah. I see you a little bit.
All right.
Hello.
Hello.
Welcome back. And okay, let me show you first. Let me show you how to do nano diffraction mapping. So first we need to find that function called experiment. Experiment. If you don't see that, you should go for workspace layout. I should be seen somewhere in the user here. And then you can just use the you just click this experiment. It drops somewhere there. So for me, I put on this one and put it here. So I can go that step window and get select experiment here. They say I can go spectrum collection and spectrum imaging. So first I need to do couple step for preparing. So I first go for let's take a look at where we are. Use the because this one is only integrated with the TA, so we can only use that for TA software. So first we go search into the detector. We go search. Screen insert. Let's open the Cornell well. Okay. So we do search. We go to TA. Let's close some image because I don't want to have too many image. It's unsaved. So probably just go close them.
Then this is turning off the diffraction button, or no?
No, we're still in diffraction mode.
Okay.
I just want to free up more space because especially when you're a TA, after some time you need to close the software, close. I don't want to save them. Okay. Okay. All right. And then go search. So first I found the region of interest. Let's say we want to do the oh, okay, this is a single crystal. Let's move to different sample. Let's go for different sample. Let's go to silicon sample. Gonna have more region of interest to take a look. Good. Okay. Let's say I want to do mapping on one of this. So what? Oh, it depends on you. First, we need to know whether you want to do converged electron diffraction mapping or you just want to do nanobeam electron diffraction mapping. So here I want to do nanobeam electron diffraction mapping. I go setting, I go to the microprobe. I choose the C2, smallest C2, which is 20. So in this case, I can do nanobeam electron diffraction. So let's say I want to do mapping over this region. So this is a good region. So first thing, I can do focusing, get a good imaging, and then I can just set up the. You need to set up the acquire imaging. So you can say acquire. It's going to acquire imaging. So once you set up acquire, okay, and then also you need to park your beam, acquire another diffraction imaging. Just like how you do nanobeam diffraction, you set up condition, you set up your theta, insert camera, you want to go for 40 frame. Let's do not go that. That's too much. Probably we can go. Let's do. Could I want to save time. Probably I just do one frame. One frame like point 0.001. What I call one frame. Okay. And then I leave the screen to see how it looks like. And then I acquire image. Three things. We definitely need more exposure. Let's go for 0.5. And then acquire image. We need more 0.1. So can make it long. So just to set up the imaging condition here, I guess I gotta. It's better just recheck the detector. Look at this is not here. Offering it. Put screen down. Okay. This is probably the region I need to do a diffraction element. Since it's small, it's bright. Okay. And then I can go acquire. Maybe we can do 10 frame. 0.1, probably 0.1. Different screen. Acquire. Okay, that looks good. Okay, and then you can just, we set up the condition, right? And then next thing, we go for experiment, select spectrum correction, spectrum imaging, go fab out, and then you add a marker. So you want to do the acquisition. And the marker means which region you want to do the mapping. So let's say I want to do mapping on this region. Okay, and then we can just go for you want to do the devel time, image size. Image size means that's your pixel size. So probably I go for 2020. Let's make it a little bigger because we can do a fast acquisition. And then once you set up that, you can just say acquire. Then it's probably going to take you to your being gonna move to position from. It's gonna acquire first. It's gonna announce. Okay. Ready screen. Yes, I leave the screen. Copy. No. Acquire sensitivity. Yes. Fast acquisition intensity. Action scale. Action scale. Probably need to set a small region. Add the marker.
You got that rectangle by clicking on add markers?
Yes. I got that rectangle add markers. And then I can go this acquire, I think. I probably need to go for single frame camera. I'll reset up that. Can go single frame. 1.1. Otherwise, it takes too much long. It takes a lot of time, so and then I can see. Okay. And then I can go for okay. Single. Okay. Go experiment again. And say setup. You need to set up acquire CCD image. Yes, that's gonna acquire your CCD, and also you want to acquire stem image. You say yes. Whether you want to close the bin after acquisition, whether you want to close the firmware after acquisition. This is for select your pixel size. We got 20 by 20. Fixed direction, you want to scan around X, or you again want to scan around Y. So develop time for the stem imaging. Let's say acquire how it looks to see how it looks like. Okay, it's getting. You see, it's gonna scan. So it seems we cannot do multiple frame. If you do multiple frame, it takes too much time. So the machine gonna be a little bit confused. So this, you just do single frame. You see this is your pixel, because I said 20 by 20, right? It's your pixel looks a little bit bigger. So basically you're gonna scan this region within this here. So right now it tells you progress. So
then each I guess each frame, each 20 by 20 pixel is showing a corresponding diffraction pattern?
Yes, corresponding the diffraction pattern on the right. And I think let's finish. And also you can select different cameras. So in this case, you can see the different view of your diffraction pattern. So here's a little bit the shortcut. So because right now I retract the detector, I think. It's retracted, so you get nothing. You get you don't get any signal from your stem, right? You see, it's basically just corresponding to nothing. But if you insert the detector, you're gonna see some cutout of your detector here. I think there you can use the HDIF, because HDIF your cutout is gonna be much bigger. You use the DF4. You probably can. Let's stop here. Let me show you. Let's stop here. Stop acquire. I don't want to finish. You can stop acquire. This is your data set. Because just now I don't insert camera. I didn't insert the detector, RF detector. Now I got a RF detector in. let's say array acquire is gonna acquire another imaging. Now you get a signal, right? In your hard image, you're scanning here, but you got a little bit of cut out there. You see, you cut off your hard detector.
Yeah.
So this is a kind of disadvantage. So
Do you do the same thing with the DF4?
yeah, probably DF4 is the better. You get a better choice. That's it. Finish a little bit more.
Okay.
So normally, let's do one volume scan, then we can stop. Definitely get a signal to scare you. If you want to get the better, even more pixel, you can see smaller image size, but that's gonna take a lot of spacing. Keep that in mind. And then I can say stop. So this is your data. You can put a bin. Let's try use DF4. Set up DF4. So you can go here insert DF4. I can recheck hard. And then I can leave the screen. I need to acquire image first. This is your hard image. This is DF4. Okay. I think we don't have signal. I think I have already. Oh, I didn't leave the screen. I need to leave the screen. Acquire image. This is your hard signal, right? Let's zoom in a little bit. Let's zoom into this region. Go search. You probably need to adjust the contrast for your scope tool. Increase the contrast. And also we need to adjust the, say if we can say that's cut out. We don't want to say that cut out, right? This should be fine. Okay, should be good. And then we can move to this region. And then say acquire. Once acquire imaging, we can set up another, keep that in mind. We need to set up another diffraction. You still see the cutout, okay. So, we don't see big difference. Because definitely DF4, you have DF4 detector is smaller than hard, but possibly you see you cut out become very smaller. So let's see. You can use DF4, but you have that cut off. Fine. You still have that cut off, you see. You say your DF4. This is your DF4. Maybe we can increase camera lens. Okay, if you increase camera lens, you're gonna see whole region. This is your diffraction. You see your detector there. I think if you want to get diffraction pattern, see clearly, you have to retract your hard disk. Otherwise, you're gonna get a cut off.
And then, okay, so for the one that you had a picture of, for the half-the, when you did the experiment, how do you see the individual diffraction patterns based on the location?
Okay, here's basically, I think here's the solution. So basically, let's go. Here, right?
Yeah. So how do you?
You can go. That's a good question. So you can select this one, this two, and put there. And you say right now you need, and then you select push the alt button in the keyboard. Press that button and then drag. Press that button and then drag this one to the diffraction imaging, CCD imaging. This will corresponding this spot with CCD, with your diffraction pattern. So, and then you can move around.
Wait, what do you do?
I just push the alt
button?
Alt, yeah, in your keyboard, ALT,
okay.
And then I push that button, and then I drag this one. I use the left mouse, drag this one to the CCD image, and then you can just move around to the corresponding position. So okay. I think I guess solution is like this. So first, because you know this kind of free imaging is corresponding to this region, right? Corresponding to this region. So you know, for this first spot is corresponding to the first spot. I think you can do kind of a calculation. You can get first you get imaging. Also get imaging, you know the pixel size of your imaging, and then you set up corresponding here. It's like image size, X and Y. You go right click. Properties, information. You know your pixel size, right? And then you set up same pixel size. Once you set up, this is for example, this one is 0.3 nanometer. You'll go for here, set up same pixel size. I think this is a unit. It's trendy. You probably need to go for this is a 20. Let's say we can match the pixel size here. This is probably around. You can match the pixel size. This is a one. This is you can go here. Information. The pixel size is about 3.1. It's 20 pixel. Data size is 20 pixel equal to, this is a calibration, 3.1, 4.4. So use this calibration, you can calibrate how much 1 pixel equal to, like for this one pixel equal to 2 divided 20, equal to 3.1 divided 20 pixel nanometer. And then you can do a kind of a math, and you figure out how much value you input here to have similar pixel size within the left image. Within the left image, so you want to say 0.3 nanometer here, right? So once you get that, you set up some image size, image wise, and then you can go, and then you can just retract your hard disk detector and do the mapping. Once you get all the mapping, you know, and then you can go, like, you still get the pixel here, right? You can go search, you can corresponding, and then you can corresponding your diffraction imaging with this image. But this image is gonna be blank image, but you're gonna within the blank image, you're gonna have pixel, right? And then then you can corresponding the pixel in the stand height in the middle image to the left image because they have similar pixel size. Am I clear? You see
Oh,
this?
so wait, can you go over that again?
So yeah, it's not a little bit complicated, but for example here because this one I take without the type detector, right?
Yeah.
So but so I let's say these two have similar pixel size. Let's say this image in the middle have same pixel size with the left image. Okay. How do we set up? They have same. How do we make sure they have same pixel size? We can go first. We can go here. We can get information. We can know the pixel size is 0.3 nanometer, and then we can go in the middle image. I can go information. I can calculate because right now this is 20 pixel, right? I input a 20 pixel. So I now want.
If you go, so this is for the 2020 is for the
middle, for the middle image.
So this 20 pixels by 20 pixels, right?
Yeah, 20 pixels.
Then the info that you did on the left, that's for the whole image, not the area that we're scanning, though.
Yeah, that's the whole image. So that's the whole image. But for the whole imaging, you can say if you look at the whole image have the same pixel size, right? So if you go this small region, and you will know the pixel size here. If you zoom in, you see this is your pixel size, right? This pixel size is about 0.3 nanometer. And then you want to make sure the right image have 0.3 nanometer in pixel size by set up the parameter here. So this is a setup like 20 pixel by 20 pixel. So now you know the 20 pixel by 20 pixel is you need to do calibration. The 20 pixel by 20 pixel is equal to this here 20 pixel equal to 3.1 nanometer. That's mean 1 nanometer. That's mean 1 pixel equal to 3.1 divided 20 nanometer. And then we need the setup. Let's do a calculation. Let's do a sample mass. I can do a sample mass very quick. So just use the one. I want to know how many nanometer we have for 1 pixel. Just one multiply 3.1 divide 20. That's gonna be 0.15 nanometer. So 1 pixel equal to 0.15 nanometer. So I want to set up like this. I know this pixel size is 0.3 nanometer. So that means we use the 0.38 and divide 0.15. So that's going to be, for the X, it's going to be about 2.5 pixel. So we set up 2.5 pixel here. Set up 2 pixel. You cannot go 2.5. It's roughly 2. And here you can set up like do the calculation probably around 3. So in this case, the left image, you make sure your left image and the middle image, they have a similar pixel size. And then you can corresponding, you zoom in that together, this, when you go select here, you zoom in. If I move this one, if I move this one to this pixel, if they, for example, if they are similar size, so if I move to So I know this one is the first pixel, right? I love first pixel corresponding to this pixel. Corresponding position here. I know this pixel corresponding to this diffraction. And then if I move here, and now and then go counting. It's gonna be 1, 2, 3, 4, 1, 2, 3, 4, and again 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's gonna be corresponding to position here. Actually, can we? Yeah, we cannot do this one. You can. So you know this diffraction is corresponding to the position here, right? Because this is a blank information. This is blank information because you don't insert the hard detector. But here you get the image. So in this way, you can corresponding your corresponding each pixel in your hard imaging to the diffraction pattern.
I think it'll be easier just to do it twice.
Just take what?
Just scan it twice. Do one with the detector.
Oh, yeah.
That way we don't have to do any complicated calculations.
Yeah, that's another way. You can take it twice. If you take it twice, that's the easy way, right?
Yeah.
Okay. Cool. Yep, you can take it twice, but that's gonna take a lot of spacing. So
okay.
Let's see. Okay.
Then so the image that you get, what kind of file image do you get from it? Is it like a stacked image, or could you view it in another software, or like?
I don't think so.
So you only view it in this software, right?
You probably can view through image J. Image J.
Image J. Okay.
Yeah. This is slide bar. You can slide through how many frames you get. So right now I already get 400 frames. You see? Okay. So each frame corresponding to 1 pixel.
Okay. Maybe there's a way in image J to like edit the image for what corresponds to what. I'll probably figure something out.
Yeah. So you probably can. This I think. So image J is it's gonna you can open image J because image J you can open a stock image, right? So if you save the data, for example, I want to save this data, you can go find, save at. Okay, okay, it's this one, yeah. Let's make sure I select the right one. So you can go save your data. You can go find, save at. You can save data. It's gonna save the EMI file.
That can open in image J?
Yeah, I think you can open that in image J, I think. You can try, but I think so. Save as probably yes. This you can only save EMI file.
You could also export it, right?
You can export.
No, like on the middle image. Could you export that?
This one?
Yeah. Because that would have all the information, or no?
This is not. This is just single image. This is just the stand image. All the information on this one. This is your CCD stocks. So you get.
So the EMI file that you saved. Does that have the image file in the middle with all the diffraction?
No.
No.
You have saved saved the individual files. I think. You have saved this one as well. Save as.
Okay, so it just saves the individual picture.
Oh no! If you open by, this is gonna save all the information. Let's say if you save, let me show you. This is gonna save all the information. But if you use image J, open it, you just see the stock of image. It's not corresponding to each pixel. Okay. But if you open with the J software, it's gonna correspond to that.
Okay.
I mean, it's just not a it's not compatible with another software. I mean, you cannot do that stuff. I'm not sure. Probably there's another like some open source online. You can use as open source. I think that's not for stuff related to the 40 stem, because people do such kind of thing by using the software like developed for 40 stem. It's similar thing. So I think you can do a little bit of research online to see if there are any open source, open software. So that's gonna handle and do a little bit more than just getting diffraction, because they can just use diffraction, and because you don't need to use the right middle image, because you only need the diffraction. And use this diffraction pattern, you can recontrast to like get together diffraction contrast imaging, and the user centered disk you can get the high imaging or different contrast imaging. So I think this diffraction pattern is most important stuff for you. You can this is stored all the information there. So this is a spectrum image, just tell you where you get that diffraction pattern. Okay. You want to do a little bit practice on this one?
Sure.
Okay. Okay. Let's do with DF4, because you guys have DF4, right?
Yeah.
So first, you're gonna do acquisition, use the DF4 with detecting, and then you do that without detecting.
Can you give me control again?
Oh, sure thing. Let me.
Okay. All right. All right. So let's go back. All right. So we'll go. DF4 is there. So let's minimize the I guess. Screen is up. We could start search. If the
You need to acquire image first. Acquire scan image, and then acquire CCD image. So then the software gonna take your setting for acquire CCD image. You need to see that software now the setting. So you first acquire that image, push that, and then you can open your TA software, and you get a scan image there, and then your acquire CCD image. Go to schema and acquire CCD image. Acquire your diffraction pattern.
okay.
It's just use one. We can just use one frame to a very fast acquisition. Okay, you see your central DF4 there, right? It's broccoli beans. Probably you can go a little bit longer exposure time. Let's do 0.1, probably integration time 0.1. Okay, let's take and then acquire another image. Okay, that's it. And then we can take the detect out, right? And then take detect out, therefore detect out, and then we can start application.
Sure.
Goes to stem. Yeah. Take it out. And then go to experiment. Select experiment. You need to go to the most right. And then go there. Select. Go to the flap out. Flap out. Add a marker first. Add a maker first. Okay, add a maker first. And then choose the image size. Probably we can go for 20 by 20. Otherwise, it's gonna take a very long time. If you go 2 by 3, it's gonna take a very long time. 20. And then you need to select acquire CCD image, yes. Acquire stem image, yes. And for the fast acquisition mode, you choose intensity. And now it's intensity. And then good. Then you can just review the position. Just select. I can just select this one. You know, this is your marker.
So when I type in 20 by 20, this size is 20 by 20?
No. The size is 20 by 20 is your pixel size.
Okay.
Each pixel. This is the region. This is your mapping region.
Okay.
You can make it bigger by push add maker. Add a maker. If I press add a maker on the left, experiment within the experiments.
Add marker is the wait.
Add marker.
I already clicked. Is this one, right?
Yeah, you can also click that one. And then you can say, you can make it bigger. Use mouse. Use your mouse, select that rectangular. And then you can make it bigger or make it smaller. And then you can move to the region of interest. Okay, you can, let's say this is the place you want to go. Then you can say acquire. So you say you're acquiring diffraction, right?
Yeah.
At each pixel. We can add it wrong a little bit. It's probably gonna take 5 to 10 minutes. So the two casing, first you need to acquire star imaging, then you need to set up your CCD camera, acquire CCD camera. So that the experiment panel, that this unit know your setting for the spectral imaging, know your setting for the CCD camera imaging, and then you're just add a marker to select the region of interest, and then you set up the image size, set up the whether you want to close the beam after acquisition or not. So all right. And then if you want to stop, you can just click cry again. It's gonna stop. Yeah, position. Okay, stop. And you see, not this one, the left one. And put in the image. Okay, and then push the out in your keyboard and drag that into the CCD image. You need to hold the out, and then drag this. Hold your left mouse and drag this one to the CCD spectrum image. Yeah. And then you can move.
Okay.
And if you select your CCD spectrum image, select your CCD spectrum image, and then you see how many frames you get. In your series, no, not this one. In the right panel, series, in the right one, in the right panel.
Oh, here?
Go up. Keep going. Keep going. Yeah, there. Keep going. Yeah, this is tell you how many slides you have. You can go left and right. And you can quick play the button. It's going to play the diffraction pattern one by one.
Okay.
All right. And then if you want to load the position, just insert the detector and do it again on the same position, right? All right. This is basically how we do the nano diffraction mapping. Next, we can. Also same thing. If you wanna just a nano diffraction, if you wanna go for converging electron diffraction patterning, you can just choose the different aperture, and then you can get a different and do the same thing. You can do
Okay.
right.
So if you didn't take the stem image, you could just slide through the diffraction graphs anyway.
You mean
the diffraction patterns? You could just do the slide number if you didn't take if I didn't take a spectrum image every single time I took the diffraction pattern.
Yeah, if you mean here, right? You can print. Yeah. Because this is a you don't have information within the F4, right?
Yeah.
Yeah. So, oh, okay. I know what you're saying. Yeah, it's possible. Yeah.
Yeah. So then.
Mm-hmm.
Okay. So I guess each of these correspond to a point, right?
Mm-hmm. You need to select that marker. Under select that's red marker. Okay. Yeah. No, it's good.
Okay. And this one over here, there's no slide number?
No, this is just a single image. You have different pixel.
Okay, so
yeah, this is you have multiple image here, but in the middle image you just have multiple pixel. It's corresponding different pixel, right?
Okay, so these are like the number or assigned to that pixel then.
Mm-hmm.
Okay. All right.
Cool. Okay, we're done with the nano diffraction pattern mapping, and then I think it's your choice. We can either do the high resolution STEM imaging, or we can go to the 10 and do the convergent electron diffraction patterning. Which way we want to go?
That's let me see. We'll work on the stem because I think you said we won't be able to see the convergence angle anyway when we do TEM, right?
Yeah.
Okay.
So you're gonna go for high resolution image, right?
For yeah.
You said that you just probably can just load the high resolution image, and then we can go over the alignment here.
Yeah.
So we load the fog register, we load the screen, we insert the hard disk.
What's a good gun and gun length and spot size?
Good gun length is for high resolution image gun length 3. Yes, just spot size 9.
Okay.
And it's you probably also can keep in mind that the screen current is 0.03. 0.0 is you have to keep your current below 100 picoamp. Okay, what the first step? I think the first step we need to do is to tilt the sample to the zone axis. So let's do preview. We go we put the sample to the zone axis because if you want to go for high resolution image, it's we have to.
So if you're looking at nanoparticles and you can't find the diffraction pattern right away, how do you do this then?
For nanoparticle, I would say either you can just look at multiple particle. It depends on how lucky you are. Sometimes because your nanoparticle is very small, it's hard to tilt the nanoparticle to the zone axis. I would say the better way is to just find more particle.
Okay.
Right? Or you have oriented particle, then it's probably easy to take high resolution TMU.
Okay.
And if your particle is like it's more than 100 nanometer, it's several hundred nanometer, probably you can do a little bit of tilting. So I would say first you pocket beam on the particle, and then you want to see your where your kick pattern is. For example, here you know your kick pattern on you probably use the smaller time length. And then in that case, you can know your capture pattern, right?
Yeah.
And then you know your cube pattern is here. You probably want to go beta alpha first, move to the center, and then you know you need to do beta tilting. So you want to move your center to the bottom, then you're gonna do negative beta tilting. So because you calculate how much the distance between center of your screen and the crossover of your cube pattern, then probably it's about, I would say right now you have beta is negative 3.9. I would say if you need to go to, based on that distance, I would get you probably go to negative 6, and you go to negative 6 directly. You don't care about your sample moving, so but go to the negative 6 first, and then you can go to find the view and then move your sample to the center again. Move.
So the 6 degrees is like based on what you think is from the center of your of the sphere.
Yeah,
from the position to the zone axis, right?
Yeah.
Okay.
Definitely the far distance, the large distance you have between them, the more tilting you need to go.
Okay.
Right? Okay. And then we can go scope to here. And then we pop a beam there. Yeah, we could go get a setting. Then hop in there and we can. Okay, it's still it's on the top, I think. Let's see. We come up here. Okay, still, I think. Oh, we tilt the observatory. Perhaps we need to go another direction. Because it seems we need to go to another direction. Probably we can go. Okay. So again, you need to spend a lot of time until the temperature zone axis. Okay, we're getting there. Then we can do a little bit of fine searching. Okay. It's close, right?
Okay.
And then we can move to the right, left. And then this is a very short command. So then you go back to normal commands. And then okay. And then we can go. We need to. Then we need to, for high resolution imaging, we need to find the morph region, and we need to do the alignment. So probably we go here. We park somewhere in the morph region. Here is a good region, and then you see high contrast, and then you click the condensed emission. You copy 1 to 2, and also you can adjust focus a little bit. You need to, as I mentioned before, you need to use the adjust condensed emission to remove any lines and find that boiling point.
And then if you when you adjust the focus, before you fix the condenser state, how do you know it's a good focus to start off with?
So basically, if I don't fix condenser, if when you go over focus, large over focus, you will see your sample area, and then if you reach the focus, you will see your basically you reach the infinite magnification. You will see the sense getting much larger. So this is with now you see you still get some condensed emission. You can do the fine focusing, do the fine adjustment.
Okay, and then this is just in nanobeam, and it's not in diffraction mode, right?
This is in diffraction mode. This is a stem mode. This is a stem diffraction mode.
Okay.
If you do stem imaging, it's gonna be in diffraction mode. Okay, and then just you see you're getting close, you probably need to adjust your position of your camera a little bit. C2 position with C2. You move to the center. You want to make sure you select the center of your kick button. Okay. Good. And then we can do a little bit of fine adjustment. Make sure this is all. This is you want to make sure you remove. Okay, this is now it's good. And then we can go to take a look at the imaging. Okay, now you see it's pretty clear. And then take a look at the defocus value. And you can push your center focus to go back to 0 defocus value. And then use Day5 to bring the sample back to focus. Okay. Okay, you stay high to bring sample back to focus. Okay, and then you can just go find the region of interest. Copy, you can do a little bit of fine setting. You make sure you're at zone axis. This downward this region probably it's good enough. If it's not good, you probably can do some maybe somewhere because you need to do very fine adjustment. Make sure your sample is not at the zone axis. Somewhere you can probably. It's gonna take time together, but this is just show you steps. how do we put a sample to the discuss array.
And so you fixed the condenser stick and everything. And then now you're looking at the zone axis again, or trying to center?
Yeah, look at the zone axis again to make sure I find the right zone axis. I guess for the high resolution, I need a perfect on zone axis. Okay, now let's close here. Once it's on zone axis, oh, here
Looks
it
like
goes.
it's
Yeah, and we can go there, zoom in the depth region. Okay, and then we can double check what it's on. Okay. This is a region, right?
Yes.
And then we use the Z to bring its code, bring it back to the code to focus. Then we can keep going. Then go here. This is good, still good enough. We can slightly adjust focus to bring back to the focus. And probably we can set up preview. So we do slow scan because and then we can go adjust condenser. A lot of vibrating there. So bring the little focus around there. A lot of vibrating. Two. Seems some contraction going around. Just a little bit scan rotation. Let's see. You see a lot of vibrating there. So I know my cosplay is not stable for some reason. Um, for some reason, there's some vibrating going on. Vibration going on.
Do we have to do any other alignments or?
This has to be good. This because I load that alignment, it's to be good. So you see now we get a lot for vibrating.
Yeah.
This is something going wrong. It's not that my cosplay is some recontraction going wrong.
Okay.
You cannot get a very high resolution imaging because I know this is something like the maintenance the highway close by.
Okay.
And Intel is close by. They have new reconstruction building going on. So you see, it's working. For now, because now it's good. You see, you can push. Let's wait a little bit. So let's wait a little bit.
Okay.
Also, another thing is for this sample because I'm not preparing this sample for high resolution imaging, so I haven't done any plasma cleaning on this sample.
Okay.
It's
That's
also
fine.
a little bit dirty. It's gonna charging. You see, when I focus being put in there, I cause some carbon deposition point there. You see here. You see her here. Probably for the hybrids, we probably needed to let's first go to different sample. Let's go to maybe you can go different sample and order.
Or I mean, I know if there's vibration, or we could just, can we look at the surface details using STEM?
Yeah, surface detail. And now think okay. Because this representation assessment also seems to be good and okay. So this is a quick check, quick like very quick method to get the HR stand. If you find that you still cannot get a good image, you probably need to go out of direction, take a look at your probe size. Take your probe, how your probe look like. Again, we need to find the, oh, okay, it's way off. It's way off. We need to do tilting. The tilting, the way. Nodes cameras. Then we can do tilting. Maybe somewhere here. We go here. Just find a different location. And then we can go for focusing. We need to just condense the image and this region is very sick. It's not a thin region. So okay. You still see that vibrating. Definitely some contraction goes around. Surgeon probably to say let's go down. Yeah, we need to find a sand region also. Go. Oh, okay, because we're at the middle of the nanometer, so probably need to go for sand region and do a little bit tilting. Let's do a quick check. It's gonna need a little bit of effort. Check the temperature axis. Okay, here you go. Go. It's moving. So. Let's go more like that. Okay. Let's go here. Staging is good. Here. Staging is good. And then we just need to focus in. Put it in focus, and then use the day to bring focus back. Okay, and then double check the scale. Okay. Um, Okay, I think probably we need to go out of direction to take a look how probe look. Oh, it's a little bit off here. So and go out of direction. It's gonna take some time, definitely. So,
Okay, so this is
Yeah.
basically once you get the zone axis and everything, you should be able to see the atoms, right, when you zoom in.
Yeah, when you should be able to see the atom, and also you need to find adjustment based on your condenser. You need to find adjustment condenser stimulation, and you need to find adjust your focusing. Another thing, it's good to check to go out of direction, and you make sure you're still, as I mentioned, and because we go through that direct element last time. So you want to make sure you got a good beam, because I haven't taken a look at that yet. I think it should be close. But let's take it. Oh, actually, it's not close. A little bit off. So I load that characteristic from that factor. It's been saved for a long time, maybe century bit. So that's the reason we need to. You see, is you need the. Oh, actually, it's way off. That means we need to go out of direction to take a look at your probe to do some fine adjustment. Now it seems we have a lot of condenser object signal to make this one round. Okay, so because we go through that last time, right? And then we set the over intensity list and make a smaller spot. And then we go PP beam point X. And then listen good. And then we move pinch to the center again. And then we need to adjust rotation center a little bit. And in rotation center, go here, you rotation center. You move that hotbar spot to the center, right? And then everything's good. Then you condense, you can go to the condenser beam again, and then you go to the diffraction mode. And you do find, and then you do find adjust your condenser, stigmatism, and the focusing based on your image. For most cases, we find you're at the sports cameras. I go to the 205, find the right cameras. And then you do diffraction element to move the screen to the center. And then you see. And then you go back to the sample, right? You find the sample, to see a sample. Use the morph. You see you pop your beam on the morph region, and then you take a look at the rankiogram. You do focusing. You see there, you got the condenser. Copy 1221. Adjust the condenser stigmatism to remove that. Go to high contrast. Remove that spot. Okay. No, it's pretty close. Okay. And then you have the region, which is the region of interest. You need to find the zone axis, right? Basically, right now everything's good. You just find a good, you find the spot that's on the zone axis. It's gonna take a little bit more time, but let's see. This is not good. Somewhere around here. Double click this region to center there. Go domain. Okay. Okay, this is a good region. Double click here. So because move to the center. Sorry. And somewhere here. And then you need to spend time on the region. It's very close to the zonguses. See now, as I mentioned, there's a lot of vibrating around. So you're so much vibration. So
I think that's good. I mean, I get the general idea
okay.
what I need to do, and then yeah, we can't look at it because of the vibration. So that's good. Okay, that's good.
Okay. This is basically how we get a good imaging, but definitely we prefer doing high resolution imaging during the night, so because there's no construction, no vibrating going around. Okay. So this is basically how we get a good high resolution imaging. Basically, you need to do some fine tuning of your condensed imaging, and also you could do the fine tuning of your focus and if you save a good refractor register, you can just load that refractor register. You don't need to go out of diffraction to take a look at your beam shape. But if you cannot get a good high resolution imaging, probably need to go out of diffraction, take a look at your beam shape. And also adjust beam to PPX and rotation center, set the intensities, and if you see you're being elongated, that means you have objective stigmatism. You use the correct objective stigmatism, and then you go to the diffraction mode, take a look at imaging, correct the condensed stigmatism, and the focus. So then you probably get a very good image. Okay. Yeah. So this is how we get our HSN, and also I guess you already know how to. So far, you already know how to do different diffraction, right? You select average diffraction, nanobeam diffraction, convergent beam diffraction. You know all the stuff, and also you know how to do nanobeam mapping, nanobeam diffraction mapping. Basically, you know how to take a high resolution TM, dark field image, bright field imaging, and also last week we go through the tomography, right? We spent one day on the 10 tomography, another day on the stand tomography, and then we did the contraction. So now you're kind of know almost everything of the Talos system. So do you have any questions?
No, I probably don't have any right now. I'll probably might send you a couple later.
Sure. Yeah, definitely. I'm happy to answer that. And it's so nice to work with you this 5 days. I know it's a bit long, but we go through so many technology. We go through tomography and the TANs, then diffraction. So yeah, now you're expert.
I think this session was pretty good this time too, because there's more hands-on.
Okay,
so
cool.
It's pretty good.
Yeah, you know, you go through everything, right? You know basically how to do that. Yeah.
Okay. All right.
All right. I wish you have a good rest of the week. And again, we're gonna have um, like a training comparison form for you to sign, and if you can leave some comment, that'd be great. And yeah, just anytime if you have any question, just shoot me an email. If I cannot respond to you immediately because sometime I'm in our training, but probably I'm gonna respond to you after the next day after I off the training. So yeah, so if you just let me know if you have more question. Okay. All right. Wish you have a good evening, and yeah, bye now.
Bye.
Yeah.